Balancing loads in an electrical panel is an important safety and efficiency consideration. It ensures that the current draw on each phase is distributed evenly to prevent overloading and potential hazards. Distributing loads prevents one phase from becoming overheated or overloaded, which can lead to electrical fires or damage to equipment. Balanced loads improve the overall efficiency of the electrical system by reducing voltage drop and power loss. The National Electrical Code, or NEC, recommends balancing loads as much as possible, especially for circuits that draw significant power. There are several strategies for balancing loads in an electrical panel. Firstly, install breakers for circuits that draw similar power on alternating phases. For example, alternate 20 amps and 15 amps breakers between the two phases. Secondly, use a phasing meter to identify the phase with the highest load. Move high current circuits to the other phase until the loads are balanced. Thirdly, electrical software can be used to simulate load balancing scenarios and determine the best circuit arrangement. In the specific situation mentioned, the electrician grouped all 20 amps and 15 amps breakers together and installed them in the panel randomly. This approach does not guarantee balanced loads and could lead to potential issues. To improve load balancing, consider the following steps. Firstly, ensure that the panel has sufficient capacity to handle the total load. Secondly, alternate the positioning of 20 amps and 15 amps breakers on the panel to distribute the load more evenly. Thirdly, if possible, use a phasing meter to identify the phase with the highest load and adjust the circuit arrangement accordingly. Balancing loads in an electrical panel is essential for safety and efficiency. While random installation may result in balancing by chance, it is recommended to implement a systematic approach to ensure proper load distribution. By following the recommended methods, the performance and safety of the electrical system can be improved. In electrical systems, single-phase power is commonly delivered using a 3-wire configuration. These wires consist of 2 hot wires, typically labeled LON and L2, and a neutral wire. The voltage between LON and L2 is usually 240 volts, while the voltage between either LON or L2 and the neutral wire is 120 volts. This setup allows for the simultaneous supply of both 120 volts and 240 volts circuits, which are used for different appliances and equipment within a building. Balancing the load across LON and L2 is crucial for several reasons. Firstly, it prevents overloading of either phase, which can lead to overheating and potential damage to the electrical system. Secondly, balanced loads minimize voltage drop, ensuring that all devices receive the correct voltage for optimal performance. Thirdly, it reduces the risk of neutral wire overload, which can occur when the current on one phase significantly exceeds the current on the other phase. To achieve balanced loads, electrical circuits should be distributed as evenly as possible between LON and L2. This can be accomplished by alternating the connection of circuits to each phase during installation. For example, a circuit drawing a significant amount of current, such as an air conditioner or electric heater, should be connected to one phase, while another high current circuit should be connected to the other phase. Smaller loads, such as lighting circuits and small appliance circuits, can be distributed more randomly, but it is still important to ensure that the total load on each phase is roughly equal. A clamp meter can be used to measure the current on each phase. This tool allows electricians to quickly and easily determine the load on each phase and make adjustments as needed. If one phase is found to be significantly more loaded than the other, circuits can be moved from the overloaded phase to the underloaded phase until the loads are balanced. Another method for balancing loads is to use a circuit breaker panel with alternating phases. In this type of panel, the circuit breakers are arranged so that each adjacent breaker is connected to a different phase. This makes it easier to distribute circuits evenly between LON and L2, as the electrician can simply alternate the connection of circuits to adjacent breakers. In addition to balancing the load across LON and L2, it is also important to consider the overall load on the electrical panel. The panel should be sized appropriately for the total load of the building, and the main breaker should be sized to protect the panel from overload. If the panel is undersized or the main breaker is too small, it is possible for the panel to become overloaded, which can lead to overheating and potential damage. The National Electrical Code, or NEC, provides guidelines for sizing electrical panels and main breakers. These guidelines take into account the total load of the building, as well as the types of appliances and equipment that will be used. It is important to consult the NEC when sizing an electrical panel to ensure that it is adequate for the intended use. In summary, balancing loads in an electrical panel is crucial for safety and efficiency. By distributing circuits evenly between low and L2, overloading, voltage drop, and neutral wire overload can be minimized. A clamp meter can be used to measure the current on each phase, and circuits can be moved as needed to achieve balance. The electrical panel should be sized appropriately for the total load of the building, and the main breaker should be sized to protect the panel from overload. Consulting the NEC is essential when sizing an electrical panel to ensure that it is adequate for the intended use. To elaborate further, let's delve into the practical aspects of load balancing in residential and commercial settings. In a typical residential setting, the electrical panel serves as a central distribution point for electricity throughout the house. It receives power from the utility company and distributes it to various circuits that power lights, appliances, and other electrical devices. Balancing the load in a residential panel involves ensuring that the current draw on each phase, low and L2, is as equal as possible. This prevents any one phase from being overloaded, which can lead to overheating, voltage drop, and potential electrical hazards. When installing new circuits or modifying existing ones, electricians typically follow a systematic approach to load balancing. Firstly, they assess the total load of the house, taking into account the wattage of all appliances and devices that will be connected to the electrical system. This information helps them determine the appropriate size of the electrical panel and the main breaker. Secondly, they distribute the circuits evenly between low and L2, alternating the connection of high current circuits to each phase. For example, a 240-volt appliance, such as an electric range or clothes dryer, is typically connected to both low and L2, drawing current from both phases simultaneously. 120-volt circuits, such as lighting circuits and small appliance circuits, are connected to either low or L2, depending on the load distribution. To ensure accurate load balancing, electricians often use a clamp meter to measure the current on each phase. This tool allows them to quickly identify any imbalances and make adjustments as needed. If one phase is found to be significantly more loaded than the other, circuits can be moved from the overloaded phase to the underloaded phase until the loads are balanced. In commercial settings, load balancing is even more critical due to the higher electrical demands of businesses and industrial facilities. Commercial electrical panels typically serve a larger number of circuits and power a wider range of equipment, including lighting systems, HVAC systems, and industrial machinery. Balancing the load in a commercial panel requires careful planning and execution to prevent overloads and ensure reliable power distribution. Electricians working in commercial settings often use more sophisticated techniques for load balancing, such as using specialized software to simulate load scenarios and optimize circuit arrangements. They also pay close attention to the power factor of the electrical system, which is a measure of how efficiently electrical power is being used. A low power factor can indicate that the electrical system is not being used efficiently, which can lead to increased energy costs and potential equipment damage. To improve the power factor, electricians may install power factor correction capacitors, which help to reduce the amount of reactive power in the electrical system. In addition to load balancing, commercial electrical systems also require regular maintenance and inspection to ensure their continued safe and reliable operation. This includes checking circuit breakers for proper operation, inspecting wiring for damage or deterioration, and testing grounding systems to ensure that they are functioning correctly. Regular maintenance and inspection can help to identify potential problems before they escalate into major electrical hazards. The National Electrical Code, or NEC, provides comprehensive guidelines for the installation, maintenance, and inspection of electrical systems in both residential and commercial settings. Electricians are required to follow the NEC when working on electrical systems to ensure that they are installed and maintained in accordance with industry standards. Failure to comply with the NEC can result in fines, penalties, and potential legal liability. In conclusion, balancing loads in an electrical panel is an essential aspect of electrical safety and efficiency. By distributing circuits evenly between low and L2, overloading, voltage drop, and neutral wire overload can be minimized. Electricians use various techniques to balance loads, including assessing the total load, alternating the connection of circuits, using a clamp meter to measure current, and employing specialized software to simulate load scenarios. Regular maintenance and inspection are also crucial for ensuring the continued safe and reliable operation of electrical systems. Consulting the NEC is essential for ensuring that electrical systems are installed and maintained in accordance with industry standards. Now let's consider specific scenarios and calculations related to load balancing in electrical panels. Firstly, imagine a residential electrical panel with a total capacity of 200 amps. The panel serves various circuits, including lighting circuits, small appliance circuits, a 240 volts electric range, and a 240 volts air conditioner. To balance the load in this panel, the electrician would firstly calculate the total load of each circuit, taking into account the wattage of all devices connected to the circuit. For example, a lighting circuit with 10 100 watts light bulbs would have a total load of 1000 watts, which is equivalent to approximately 8.3 amps at 120 volts. Secondly, the electrician would distribute the circuits between low and L2, alternating the connection of high current circuits to each phase. The 240 volts electric range, which typically draws a significant amount of current, would be connected to both low and L2. The 240 volts air conditioner would also be connected to both low and L2. The lighting circuits and small appliance circuits would be distributed between low and L2, ensuring that the total load on each phase is roughly equal. To verify the load balance, the electrician would use a clamp meter to measure the current on each phase. If one phase is found to be significantly more loaded than the other, circuits can be moved from the overloaded phase to the underloaded phase until the loads are balanced. Secondly, consider a commercial electrical panel serving a retail store. The panel powers various circuits, including lighting systems, HVAC systems, cash registers, and display cases. To balance the load in this panel, the electrician would firstly calculate the total load of each circuit, taking into account the wattage of all devices connected to the circuit. For example, a lighting system with 50 fluorescent light fixtures, each drawing 40 watts, would have a total load of 2000 watts, which is equivalent to approximately 16.7 amps at 120 volts. Secondly, the electrician would distribute the circuits between low and L2, alternating the connection of high current circuits to each phase. The HVAC systems, which typically draw a significant amount of current, would be connected to both low and L2. The lighting systems, cash registers, and display cases would be distributed between low and L2, ensuring that the total load on each phase is roughly equal. To verify the load balance, the electrician would use a clamp meter to measure the current on each phase. If one phase is found to be significantly more loaded than the other, circuits can be moved from the overloaded phase to the underloaded phase until the loads are balanced. In addition to balancing the load between low and L2, the electrician would also ensure that the total load on the panel does not exceed its capacity. The panel's capacity is determined by the size of the main breaker, which is typically specified in amps. If the total load on the panel exceeds its capacity, the main breaker will trip, interrupting the power supply to the store. To prevent overloads, the electrician would carefully manage the load on the panel, ensuring that the total current draw does not exceed the main breaker's rating. Furthermore, let's examine how to calculate voltage drop and its impact on load balancing. Voltage drop is the reduction in voltage that occurs along an electrical circuit due to the impedance of the wires. Excessive voltage drop can cause appliances and equipment to malfunction, reduce their efficiency, and even damage them. To calculate voltage drop, electricians use a formula that takes into account the length of the circuit, the current flowing through the circuit, and the impedance of the wires. The formula is as follows: voltage drop equals 2 times current times length times impedance divided by 1000, where voltage drop is measured in volts, current is measured in amps, length is measured in feet, and impedance is measured in ohms per 1000 feet. For example, consider a 120-volt circuit that is 100 feet long and carries a current of 15 amps. The wire used for the circuit is 12 American wire gauge, or AUG, copper wire, which has an impedance of approximately 2 ohms per 1000 feet. Using the voltage drop formula, the voltage drop in this circuit would be calculated as follows: voltage drop equals 2 times 15 amps times 100 feet times 2 ohms per 1000 feet divided by 1000 equals 6 volts. This means that the voltage at the end of the circuit would be 114 volts, which is 6 volts lower than the source voltage of 120 volts. The National Electrical Code (NEC) recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. A branch circuit is a circuit that supplies power to individual outlets or appliances, while a feeder is a circuit that supplies power to multiple branch circuits. In the example above, the voltage drop of 6 volts represents a 5% voltage drop, which exceeds the NEC recommendation for branch circuits. To reduce the voltage drop in this circuit, the electrician could use a larger wire size, such as 10 American wire gauge, or AUG, copper wire, which has a lower impedance. Alternatively, the electrician could shorten the length of the circuit or reduce the current flowing through the circuit. Voltage drop can also be affected by load balancing. When loads are not balanced, one phase may experience a higher voltage drop than the other phase. This can cause appliances and equipment connected to the overloaded phase to malfunction or operate inefficiently. To minimize voltage drop, it is important to balance the loads as evenly as possible between load and L2. Let's discuss practical methods for balancing loads in the distribution panel using readily available tools and techniques. Firstly, visual inspection of the breaker arrangement can provide a preliminary indication of load distribution. Observe if breakers of similar amperage ratings are alternated between the phases. A pattern of alternating breakers suggests an attempt at load balancing, while a grouping of breakers of the same amperage may indicate an imbalance. Secondly, utilizing a clamp meter is a straightforward method for measuring the current on each phase. The clamp meter is non-invasive, allowing measurements without disconnecting any wiring. Clamp the meter around the main feeder wire for each phase to obtain a reading of the current being drawn. Compare the readings for each phase. Significant differences in current levels indicate a load imbalance. Thirdly, circuit tracer tools can aid in identifying which circuits are connected to each phase. These tools typically consist of a transmitter and a receiver. The transmitter is connected to a circuit, and the receiver is used to trace the path of the circuit back to the distribution panel. By tracing several circuits, you can determine which phase each circuit is connected to and identify any potential imbalances. Fourthly, load calculation spreadsheets or software can assist in analyzing the total load on each phase. Input the amperage ratings of all the breakers connected to each phase. The spreadsheet or software will then calculate the total load on each phase, providing a clear picture of the load distribution. Fifthly, power quality analyzers are advanced tools that can provide detailed information about the electrical system, including voltage, current, power factor, and harmonic distortion. These analyzers can help identify subtle load imbalances and other power quality issues that may not be apparent with simpler tools. Sixthly, thermal imaging cameras can be used to detect hotspots in the distribution panel. Hotspots may indicate overloaded circuits or loose connections, both of which can contribute to load imbalances. Scan the distribution panel with the thermal imaging camera and look for any areas that appear significantly warmer than others. Remember that safety is paramount when working with electrical systems. Always energize the circuit before making any connections or measurements. Wear appropriate personal protective equipment, or PPE, such as safety glasses and insulated gloves. If you are not comfortable working with electrical systems, consult a qualified electrician. In addition to these practical methods, there are also several theoretical considerations that can help improve load balancing. Firstly, diversity factor is the ratio of the maximum demand of a system to the sum of the individual loads. The diversity factor takes into account the fact that not all loads will be operating at their maximum demand simultaneously. Using the diversity factor, you can more accurately estimate the total load in the electrical system and design the system accordingly. Secondly, the concept of power factor correction can significantly improve the efficiency of the electrical system. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that the electrical system is not being used efficiently, which can lead to increased energy costs and voltage drop. Power factor correction capacitors can be installed to improve the power factor, reducing energy costs and improving voltage regulation. Thirdly, harmonic mitigation techniques can reduce the distortion of the voltage and current waveforms in the electrical system. Harmonics are caused by nonlinear loads, such as electronic devices and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, increased energy costs, and interference with communication systems. Harmonic filters can be installed to mitigate harmonics, improving the power quality of the electrical system. In summary, balancing loads in an electrical distribution panel is a crucial aspect of electrical safety and efficiency. By using a combination of practical methods and theoretical considerations, you can ensure that the electrical system is operating at its optimal performance. Always prioritize safety when working with electrical systems and consult a qualified electrician if you have any concerns.